All right, welcome to multi-level queue scheduling practice. I already did this assignment with PowerPoint animation, but I'm going to do this exercise again with writing on the screen, and it might be a little clearer to understand. So this is the same exercise. We have multi-level queue, which means that the processes do not move between the queues. So if it's a Q1, it's going to remain a Q1 throughout the entire time it's active in the system, and if it's a Q2, it will remain a Q2 the entire time it's active in the system. So that's the difference. In feedback, you might have different reasons for them to move between different queues, maybe for time quantum, maybe for aging. So there's all, and the rules are just set up by however you set them up to be, the policies that you make for your system. And in this case, we have 5 processes, which are Q1 and Q2, and Q1 has round robin with a time quantum of 4, and Q2 has a round robin with a time quantum of 3. So let's get started. Let's just remember that, just to remind us that, oops, I gotta get my pen here. All right, so just to remember that Q1 is round robin with a time quantum of 4, and Q2 is round robin with a time quantum of 3. So I'm going to go down here, draw my Gantt chart, and we'll get started at time 0. So at time 0, if we take a look up here, we can see that the only one that has arrived at time 0 is P1. So P1 will go first. And P1 is a Q2 process. You can see here it's a Q2 process. So therefore, it does round robin with a time quantum of 3. Now, since it's a Q2, we also need to check at every time unit to see if there's an arrival of a Q1. And we can see by looking that there is no Q1 arriving in the first 3 time units. So P1 is going to finish at time 3. So what happens when P1 finishes at time 3? It's going to go back into the ready queue at time 3, and it's going to have 7 time units of CPU burst left. So now we are at current time 3, and we need to take a look. And of those that have arrived and are active in the system at this time, there's P1 and P2. All the rest have not arrived yet, as you can see here by their arrival times. So what we're going to do now is we're going to have P2 go next. And since P2 is a Q1 process, it does round robin with a time quantum of 4. So P2 will go until time 7. Now the current time is 7. The only ones active still in the system now are P1, P2, and now P3 has arrived, but P3 is also a Q2, so therefore P2 is going to continue, and P2 will do the other 3 time units. Oops, I messed up on that. That should be a 10. P2 will do the other 3 time units, and now at time 10, P2 has completed its execution. So we have P2 is done at time 10. All right, so now the current time is 10, and in our ready queue, we have P1, which is a Q2, we have P3, which is a Q2, and both P4 and P5 have not arrived yet. So now, in order to decide which one goes next, we have 2 that are the same priority, and so we use first come, first serve to break that tie. So we're going to have P1 go first. So P1 is going to go, and when P1 goes, P1 will should get 3 time units of CPU burst. However, if you notice, there will at time 12 we will have the arrival of P4, and P4 is a higher priority. So P4 is going to arrive at time 12, and at time 12 P1 is going to be preempted, not for time quantum, but because a higher priority task has arrived. So what we need to do now is we need to again mark here that P1 has a new arrival time at time 12 and has completed 2 more of its CPU bursts, so it has 5 time units of CPU burst left. So now the current time is 12, and since P4 is a level 1 process, it will not be preempted by any other process. So P4 will go now, and we'll get 4 time units until time 16. And if you notice, P5 has not arrived yet, but if P5 had arrived like at time 14 in here, then P5 would go before P4. But since P5's arrival time is 18, P4 will go again and will complete its last CPU burst. So now P4 has completed all of its execution and is now done at time 17. All right, now the current time is 17, and in the ready queue, we have P1 that got there at time 12, P3 that got there at time 4, and P5 that got there that has not arrived yet. So both P1 and P3 are level 2 processes, and since P3 got there at time 4, we will have P3 go next. But if you notice what's going to happen, at time 18, we will have the arrival of P5. And P5 is a higher priority task, so therefore P3 will be preempted at time 18. So we need to put that P3 has a new arrival time at time 18 and has 5 time units of CPU burst left. And we will notice now that P5 is a higher priority, and so P5 will now get the CPU. So we will run P5, and P5 gets 4 time units, so it will go until time 22. And since at time 22 there are no other level 1 processes in the ready queue, P5 will continue and will finish execution at time 26. And now we have only 2 processes left in the ready queue. We have P1 and P3, and since P1 and P3 are the only 2 that are, we'll just, let's mark off P5 so we can indicate it's completed its execution. And now we will just do regular round robin with a time quantum of 3 to finish off P1 and P2. So if you take a look, we have to look at arrival time. P1 got there before P2. P1 got there at time 12. So we will start with P1. P1 will get 3 time units because it's a level 2. It will go until 29. And then you can see it has used up 3 of its CPU bursts, so it will have 2 left. Then we have P3, which will go until time 32. And then we have P1, which will finish up its last 2 time units of CPU burst, 34. And then we have P3, which will finish up its last 2 time units of CPU burst and be done at time 36. And if you add up all of these CPU bursts, 10, 17, 23, 31, 36, you will see, since we have 100% CPU utilization, we will also have the amount of time that this simulation takes is going to match the CPU bursts. All right, so now we can calculate, once we get this done, we can calculate our response times, wait times, and turnaround times per process. So to calculate the response time, you just go from the time it arrived to the very first time it gets on the CPU. So P1 arrived at time 0, first got on the CPU at time 0, so P1's response time is 0. P2 arrived at time 3, waited 4 time, got right on the CPU at time 3, so has a response time of 0. P3 arrived at time 4 and actually had to wait until time 17 to get the first time on the CPU, so it has a response time of 13. P4 arrived at time 12 and had to wait no time. It didn't wait at all because it was a level 1 and preempted, so P4's response time is 0, and P5 also preempted, so P5 has a response time of 0. Then to get the turnaround time, you go to the last entry and you subtract the arrival time. So P1 finished at time 34, so therefore P1's turnaround time is going to be 34 since P1 arrived at time 0. P2 finished at time 10 arrived at time 7, so P2 has a turnaround time of, arrived at time 3 has a turnaround time of 7 time units. All of those 7 time units were spent on the ready queue, so therefore, all of the 7 time units spent executing using its CPU burst, so therefore P2 never waited at all. P3 finished at time 32 here, arrived at time 4, so P3 finished at time 36 here, arrived at time 4, so P3 was active in the system for 32 time units. P4 arrived at time 12 and finished at time 17 and was active in the system for 5 time units. All that time doing CPU bursts, so P4 never waited at all for anything. P5 was active in the system for the entire time as well, which was 8 time units on the CPU the entire time. So the only ones that accumulated additional waiting time were P1 and P3, which makes sense because P1 and P3 are lower priority. So one way that you can do this is you can take the total time and subtract the CPU burst time, and that will give you the wait time because a process is only either on the CPU or waiting for the CPU. So this would be 24, and you could take the total time that P3 was active and subtract the 6 time units of CPU burst, and you would get 26 time units of wait time. The other way to calculate the wait time is to add it up. So you take the response time, which is the first measure of wait time. So for example, for P1, you would take the response time, which is 0, and then add any additional waiting time together, and you would get the total wait time. So P1 waited from here to here, and then P1 waited again from here to here, and then P1 waited again from here to here. So P1's response time, it waited 0 time units, but then it waited 7 time units here, and then P1 waited from 12 to 26, which is 14 time units here, and then waited again from 29 to 32, which is 3 time units here. So if you add that up, 7 and 14 and 3, you would get the 24 time units of P1's wait time. And you would have 0 plus 7 plus 14 plus 3. And if you wanted to do the same thing for P3, you would take the response time, which is 13 time units, and then you would add any other time that P3 waited, which P3 waited 14 units response time, and then waited here, which is 11 more time units, and then waited here, which is 2 more time units. So if you have 13 plus 11 plus 2, and this is the response time. It's the first measure of wait time. 13 plus 11 plus 2 equals 26, which is the total wait time for P3. So I hope that this helps you to understand a little better how multi-level queue works. Keep in mind that in multi-level queue, when a process goes into a queue, it remains in that queue for the entire time it's active in the system. And just here on this next slide is just a neater version of the same thing that we just did, and I will put a PDF of this on Blackboard for you to take a look at it. This is the work, and then this is the results.